Hi everyone, welcome to meeting 11 of Cryptography Club. We're going to talk about determining coprime, greatest common divisor, least common multiple, and Bézout's theorem. Why do we need to find coprime numbers? We need to find them because one of the restrictions for public key E is that E must be coprime with phi n. So when we're trying to find public key E, we need to find coprime numbers. There are 5 methods to determine coprime. 1 is conceptual by using the definition. 2 is patterns because there are certain rules that can be used and certain numbers that has to be coprime with each other. The 3rd method is decomposition, which is using prime factorization. The 4th one is by using the difference. When the two numbers have a small difference, we can use this method. The 5th one, when the two numbers have a big difference, then we can use the quotient method. The first one is the conceptual method. Two numbers only have a common factor of 1 are called coprime numbers. So we could use this definition to determine if two numbers are coprime. For example, 9 and 11 only have a common factor of 1, so they are coprime. Next is the patterns method. The first pattern is two non-identical prime numbers are coprime. For example, 7 and 11, 17 and 31 are coprime. Because they are prime numbers, that means they only have a factor of 1, so they won't have any common factors that aren't 1. So any two non-identical prime numbers are coprime. The second one is two consecutive natural numbers are coprime. For example, 4 and 5 are coprime, 13 and 14 are coprime. 3. Two consecutive odd numbers are coprime. For example, 5 and 7, 75 and 77 are coprime. 4. 1 is coprime with any natural number. So 1 is coprime with 4, 1 is also coprime with 13, and any other natural number. 5. If the larger of the two numbers is a prime number, the numbers are coprime. For example, 3 and 19 are coprime, 16 and 97 are coprime. Because if the larger number is a prime number, then it can't have any common factors with the smaller number. So because 19 is a prime number, 3 is coprime with it. Also, 97 is a prime number, so 16 is coprime with it because it is smaller. 6. If the smaller of the two numbers is a prime number, plus the larger number is a composite number and not a multiple of the smaller number, the two numbers are coprime. For example, 2 and 15 are coprime because 2 is the smaller number and it is a prime number, and the larger number 15 is a composite number, but it isn't a multiple of 2 because the only factors it has are 1, 3, 5, and 15. So 2 and 15 are coprime. 7 and 54 are coprime because 7 is a prime number and 54 is a bigger composite number but does not have a factor of 7. Number 7. If the larger number is 1 more or 1 less than 2 times the smaller number, the two numbers are coprime. For example, 13 is coprime with 27 because 13 times 2 is 26, and then 26 plus 1 is 27. Similarly, 13 is also coprime with 25 because 13 times 2 is 26, and then minus 1 is 25. Those are all of the patterns. The next method is the decomposition method. If both numbers are composite, which means that they aren't prime numbers, we first prime factorize the two numbers and then check if they have any common prime factors. If not, the two numbers are coprime. For example, 130 and 231. We first prime factorize them. 130 equals 2 times 5 times 13, and 231 equals 3 times 7 times 11. And we can see that they don't have any common prime factors. Therefore, 130 and 231 are coprime. The next method is the difference method. If there's a small difference between the two numbers, we can first find the difference, and then see if the difference is coprime with the smaller number. If they are coprime, then the two numbers are coprime. For example, 194 and 201 are not that far apart because their difference is only 7. So we find the difference, which is 7, and then compare it with the smaller number and see if 7 is coprime with 194. And it is, so 194 is coprime with 201. We can see if 7 is coprime with 194 using the other methods like the pattern method or the conceptual method. The quotient method is used when the two numbers have a big difference, because if they have a big difference, then using the difference method is not much different from just comparing the two numbers by themselves. So when we're using the quotient method, we divide the larger number by the smaller number. If the remainder is coprime with the smaller number, then the original two numbers are coprime. For example, 317 and 52. When we divide 317 by 52, we get 6, remainder 5. So we compare the remainder with the smaller number. So 5 is coprime with 52. So 52 and 317 are coprime. Those are the methods for determining if two numbers are coprime. Next is the greatest common divisor and the least common multiple. The Euclidean algorithm is the most used for finding the greatest common divisor of two numbers, and it is efficient. The number of steps the algorithm takes is at most 5 times the smaller number. 5 times the smaller number may seem like a lot of steps, but it isn't compared with stuff that have like smaller number to the power of 10 amount of steps. So because it's not squaring it or anything, it's just timesing it by 5, so the number of steps is very little. The greatest common divisor is usually expressed in parentheses. So a comma b in parentheses means the greatest common divisor of a and b. The least common multiple is expressed by square brackets. So a comma b in square brackets means the least common multiple of a and b. There are 2 rules. If the greatest common divisor of a and b is 1, then the least common multiple of a and b is the product of a and b. And a and b, a is coprime with b. Because if the greatest common divisor of two numbers is 1, that means that they don't have any common factors. So their least common multiple has to be the product of themselves together. And they are coprime because the definition of coprime is that they only have one common factor of 1. So if a and b's greatest common divisor is 1, then they are definitely coprime. The second rule is that if a and b's greatest common divisor is d, then a divided by d and b divided by d has a greatest common divisor of 1. So if a and b have a greatest common divisor of d, then when we divide a by d and b by d, then we take out all of the d parts of it. So their greatest common divisor has to be 1. The relationship between the greatest common divisor and least common multiple can be expressed simply by the greatest common divisor of a and b times the least common multiple of a and b equals the product of a and b. By using this equation, we can have a quick way to calculate the least common multiple of two numbers. And we're going to use that in the code. Next is Bézout's theorem. This is an important theorem for studying the greatest common divisor and least common multiple. It is the foundation of RSA. Bézout's theorem states that if a and b has a greatest common divisor of d, then there are integers x and y that satisfy ax plus by equals d, and there is an infinite amount of integers x and y. When ed plus k times phi n equals 1, 1 is less than e, which is less than phi n, and e is coprime with phi n, then d and k will have a smallest positive integer solution. Specifying a and b, we can use the extended Euclidean algorithm recursively to satisfy x and y of the equation ax plus by equals d. So if we know what a and b is, then we can definitely find x and y by using this equation, ax plus by equals d. Next, let's look at the code. Here is the code for coprime and greatest common divisor and least common multiple. We have two functions. The first one is for determining coprime. The name is mutual prime and the parameters are n and m. These are the two numbers that we're going to compare. So the value of n and m does not matter, so you don't have to make n the smaller one or m the smaller one. For example, n can be 15 and m can be 5, or n can be 5 and m can be 3. They both work. Inside the function, the first line is t equals 0. This is the initialization. And then after that, we have a while loop. While m is greater than 0, t is given the value of the remainder of n divided by m. And then the value of m is given to n, and the value of t is given to m. And then we print m, and then the value of m, and then n, the value of n. So if t equals 0, then m equals 0, and then the loop stops. So if t equals 0, that means that n divided by m has a remainder of 0, and that means that they are not coprime, because when something has a remainder of 0, then it is the factor of one of them is the factor, one of the numbers is a factor of the other number. So then the loop breaks. But as long as the remainder of n divided by m is not 0, t will not equal 0 and m will not equal 0, and the loop continues until m equals 0. When m equals 0, the loop breaks, and then we go into the if statement. If n equals 1, that means that the two numbers are coprime because their only common factor is 1, and then we return true. Else, so if n equals any other number, then we return false, because that means that the two numbers n and m have common factors that aren't 1. So let's try running the code. Here we have n equals 13 and m equals 765, and then we run the function with these two numbers. So first, n equals 13, m equals 765. It comes into the function. The first print prints m and n. So the first time, m equals 13 because n divided by m, which is 13 divided by 765, has a remainder of 13. And then it printed the value of n, which is the past value of m, which was 765. So n is 765 here. In the second time of the loop, m becomes 11 because m is the remainder of n divided by m. So 765 divided by 13 has a remainder of 11. So that's m. And then n is the smaller of the two numbers from the past loop, which is 13. And then similarly, in the third loop, 13 divided by 11 has a remainder of 2, so that was given to m. And then n is given the value of the previous smallest number, which is 11. In the fourth loop, m is the remainder of 11 divided by 2, which is 1. And then n becomes the previous m, which is 2. In the fifth loop, 2 divided by 1 has a remainder of 0, so m becomes 0, and then n becomes 1. So now m has become 0, and the loop stops in the function. And because n equals 1, the function returns true, which means the numbers are coprime. So here, the value of result variable is true. So if result, print the two numbers are coprime. So this line gets printed because result is true. That's for determining if two numbers are coprime. Next, let's look at the function of finding the greatest common divisor and least common multiple. This function takes in parameters a and b. In the initialization, m is given the value of a, n, b, and 0 is given to c. C is the remainder in this case, and it is given 0 just for the initialization part. And then we print c, m, and n. And then there's a while loop again. While n doesn't equal 0, the remainder of m divided by n is given to c, the value of n is given to m, and the value of c is given to n, and then we print c, m, and n. As long as n doesn't equal 0, this loop continues. As soon as n equals 0, that means c equals 0, which was the remainder of m divided by n. That means that n becomes a factor of m, and then that means we have found the greatest common divisor. And then the loop just stops. The function returns m, which is the greatest common divisor, and the integer of a times b divided by m, which is the least common multiple. We used the formula for least common multiple here to get the result very easily. And then when we run the code, we used 12 as a and 2 as b. So it's going to find the greatest common divisor of 12 and 2 and the least common multiple of 12 and 2. And then we print them. So here we got the results that the greatest common divisor is 2 and the least common multiple is 12. And then we have these two other lines from inside the function. So the first print is c, m, and n. That was before any of the calculation was done. C was 0, which we defined here. And then m is a, which is 12. So m is 12. And then n is 2, because b was given to n. And then the second line is from inside the while loop. So m divided by n's remainder is given to c, because m equals 12 and then n equals 2. 12 divided by 2 has a remainder of 0, so c becomes 0. And then the value of n is given to m, so m becomes 2. And then c is given to n. C was 0 from the previous one. No, c was 0 because it is the remainder of 12 divided by 2, and then that was given to n. Because n becomes 0, the loop stops, and it returns m, which is the greatest common divisor, as 2, and then the integer of a times b divided by m, which is 12 times 2 divided by 2, and that equals 12. So that's how we got the greatest common divisor and the least common multiple. That's everything for the code. At the bottom, there is some more information, but it is all been covered in the PowerPoint. So if you want to look at the code and the PowerPoint at the same time, you can just scroll down and look. Oh yeah, this is more explanation for the variable. So this is the logic for it. When we have integers a and b, there are 3 steps we use to find the greatest common factor. First, we do find the remainder of a divided by d, which is c. If c equals 0, then b is the greatest common factor, because when the remainder is 0, that means a can be divided by b, so b is the greatest common factor. So then we have found the greatest common factor. But in the third step, if c doesn't equal 0, then we give the value of b to a, give the value of c to b, and then repeat from step 1. And we do this until c equals 0. When c equals 0, the b is the greatest common factor. So that's how this part of the code worked. Thank you.